we're good to go.
All right. Thank you very much, Roy. And thanks everyone for your time, and welcome to this session on spanner migration. So good afternoon to everyone in the West Coast, and evening if you're on the East Coast. And I'm actually from Sydney, so it's morning here. I'm Nevin Heintze. I'm a senior engineer at Google working on Spanner, and my focus is on database migration. So today we're going to discuss migration to Spanner, and I'm going to give an overview of typical steps in a migration, and then we're going to do a deep dive into some of the core parts of a migration, and then I'm going to describe best practices and also some migration tools. Now, just a heads up, I think we advertise this as 30 minutes. I probably have actually about 25 minutes of material. So with questions, just sort of a heads up and an apology in advance. We're probably going to spill a little bit over the 30 minutes. So we might get to 35 or 40 minutes. So apologies in advance. Okay. So here's a typical set of steps in a migration. And these steps are fairly independent of the source and target databases involved. And I'm sure for some of you, these steps will be very familiar. What I'm going to do is go over these steps and highlight them from the perspective of migrations to Spanner. And I'm particularly going to focus on migrations from MySQL to Spanner. Most migrations start with some kind of assessment phase. And the goal here is to determine if the target database, in this case Spanner, is likely to be a good fit. Will it provide the necessary functionality? Will it meet the performance, the cost performance requirements? How much work will the migration be? What are the biggest risks? What are the biggest benefits? The next step is often a proof of concept. And in many ways, this is sort of an extension of the assessment. So it's typical for a proof of concept to focus on key items that come from the assessment, like what are the biggest risks, or confirming that the main benefits of the migration can be delivered. So for example, many Spanner users see Spanner's ability to scale as one of its main benefits. And so their POCs often focus on evaluating Spanner's ability to scale for their use case. The next step, step 3 on this slide, is the core part of the migration preparation. So the design and implementation of the migration. This can have many components, but there are 3 common themes. The first is designing an appropriate Spanner schema. The next is determining how data will be moved from MySQL to Spanner, and building components to support this move. And the third is application changes to switch over to using Spanner. This can range from migrating queries to code changes to switching from MySQL's APIs to using Spanner's APIs, and it could potentially involve application modernization. The next step, step 4, is testing and dry runs. Now, successful migrations involve significant testing, either using test traffic or parts of your production load. And it's common for these 2 steps, steps 3 and steps 4, to be intermixed. So you might have an initial design and an implementation, try it out, find issues, and then go back and do some redesign, change some implementation. Maybe you find a performance issue and you need to go back and tweak the schema and, for example, add an index. So this is really an iterative process between steps 3 and 4. Now, many migrations have a target day for moving data or for completing the move and switching over to using Spanner. So this becomes a really critical day, a convergence of all of the planning and execution phases of a migration. And there's usually a substantial amount of planning around what happens on this day with detailed schedules, kind of all hands on deck situation. And a key part of this is knowing how to respond if things don't go according to plan. What signals and dashboards should we be looking at? What's the criteria for reverting? How do we revert? Now, I want to emphasize that all of the steps I've listed here, you shouldn't take this as too prescriptive, because every migration is going to be different. And which steps are important, which have the biggest risks, which take the most time, will vary significantly from one migration to another. All right, so over the next few slides, I'm going to do a deep dive into each of these steps. So as we discussed earlier, Most migrations start with some kind of assessment phase. And there's a basic question we want to answer. Is Spanner a good choice? A common starting point is an analysis of what MySQL features are actually being used, what types and indexes and queries are used, what about stored procedures, stored functions, what about auto increment? And based on this analysis, we need to determine how well these features map onto Spanner. So Spanner supports most core types, but not some of the more exotic types, geometry types, and point types that MySQL has. Spanner also doesn't support stored procedures, and the usual solution there is to pull that functionality into application code. Auto increment and sequences are not supported in Spanner either, and these are challenging to handle at scale because of the hotspots they can generate. We recommend using random generation of IDs to spread the load across the key space, and there are several other alternatives. There are differences between the query dialect of MySQL and Spanner. So for some migrations, query translation is a really critical component. Now, it's worth emphasizing that there's a huge variation here between different MySQL users. Some use a very broad set of MySQL features, and others essentially only use MySQL as a key value store, just using very basic types. Now, one trend we've observed for MySQL users who want to migrate to Spanner is that they typically have very large MySQL databases, and they're hitting MySQL scalability limits. They're often using sharding and have multiple MySQL replicas. As a result, they often limit their use of MySQL features that don't scale well, such as stored procedures, triggers, auto increment. And they often have very highly optimized queries, especially for their core high QPS operations. So this often minimizes the role of complex queries, complex joins, and full table scans. I want to briefly touch on transaction semantics and locking. So those of you who are familiar with MySQL will know that this is a really complicated topic. The default MySQL isolation level is repeatable reads, and most MySQL servers run with this default. This isolation level does indeed provide repeatable read semantics for standard SQL queries. However, the picture gets much more complicated for DML statements and for SQL queries that acquire locks. Such statements are essentially executed using read committed semantics. So it's not uncommon for MySQL users to employ sophisticated locking strategies to ensure the transaction semantics they need, or to implement safety checks to identify and correct anomalies due to, for example, lost updates or read or write skew. Now, in contrast, Spanner provides a simple, robust transaction model, which is serializability. So all transactions appear if they were executed in serial order, even if some of the reads and writes of distinct transactions actually occur in parallel. In other words, anomalies like lost updates, random reads, read skew, write skew, and so forth don't happen in Spanner. This can significantly simplify code for managing locks or for managing MySQL transaction anomalies. Now, note that transactions do occasionally fail and are rolled back in Spanner and have to be retried. So it's really important that your code base and the libraries you use, that together they provide the appropriate retry logic. Okay, so another important aspect of assessment is looking at how your applications communicate with MySQL. What drivers do they use? Do they use ORMs? Are those supported by Spanner? Finally, an assessment usually contains an analysis of the benefits of using Spanner. So what are the key features that are driving the adoption of Spanner? It might be scalability, or that Spanner is a fully managed service with no downtime, or it may be just the high availability of Spanner, that it provides 4 nines uptime for regional instances and 5 nines uptime for multi-region configurations. We'll talk a little more about Harbour Bridge later, but I want to note here that one of the core features of Harbour Bridge is that it automatically generates an assessment report from a MySQL database. All right, so moving on to step 2. As we noted before, it is typical for a proof of concept to almost be an extension of an assessment. So the role of the POC is often to scope out the biggest risks, validate the main benefits. And it's quite common for a Spanner POC to focus on scalability, to establish that Spanner can scale to your needs and workload. Given Spanner's virtually unbounded scalability capabilities, demonstrating this is not usually an issue, although we have seen some cases where hidden limitations or constraints on the customer side can lead to apparent scalability limits. And then it's a matter of debugging the system end-to-end to find out where in the customer stack the issue is, or in network configuration, and so on. Another aspect of the POC is figuring out sizing estimates. So how many Spanner nodes will be required for the workload? Sizing of any database is workload dependent, and Spanner is no exception. We provide some rules of thumb for basic workloads, but we always strongly recommend that you run tests with your workload, and this is often part of the POC. Implicit in most POCs is learning about Spanner. So it's common for our users to get valuable Spanner experience during the POC and build their level of comfort and confidence that Spanner will work for them. A couple of high-level planning aspects of a POC that are worth mentioning. So it's really important to establish a clear scope of the POC. Don't try to address all issues and solve all problems, but it's critical to limit the scope to just the important issues. And of course, to have a well-defined and realistic success criteria for the POC. The next step, step 3, is the core part of the migration preparation, the design and implementation of the migration. Now, there's a lot we could talk about here, but I'm going to focus on 3 common tasks: schema migration, data migration, and application migration. And we're going to talk about schema migration first. That is, what we want to do is design an efficient Spanner schema to meet the application and workload needs. Now, the starting point here is usually types and columns and tables to support the application needs. But really critical elements of the design are around primary keys. So these have to be designed for scalability and in particular to avoid hotspots. And of course, they need to be designed to be appropriate for the query load. So it's not uncommon for problems to surface months after a migration that can be tracked back to issues with primary key design. So this is a really critical thing to get right. Much of schema design is driven by query performance. So the role of secondary indexes is very critical. And Spanner provides some unique capabilities to optimize queries. So for example, using interleaved tables to control the layout of data between related tables. And this can provide significant query performance boosts for joins as well as for writes. Inherent in schema design is managing trade-offs, such as the cost of reads versus the cost of writes. For example, I might add a secondary index to improve my read performance, but this means that my writes will become more expensive. So in Spanner, a secondary index is implemented as a Spanner table. So when I add a secondary index to a table, then any row I add to that table actually adds 2 rows. It adds 1 row to the base table and another one to the index table. So if I have many secondary indexes, then my writes can become very expensive. And it's really critical to balance these trade-offs. And this is particularly true if you're moving from MySQL, where the balancing in costs between indexes and reads is a little different. So this is something that, coming from a MySQL background, pay particular attention to. The next task we're going to discuss is data migration. And we could have a whole workshop on data migration. So I'm only going to skim over some really high-level choices here. In short, there are many alternatives. But in most cases, business needs or application architecture will quickly narrow down the choices that you have. So I'm just going to start with the simplest, most basic migration strategy, which is stop and copy. So obviously a big downside here is that you need to stop your application for a period of time, maybe a few hours or more. And the basic idea is stop everything, copy over all the data from MySQL to Spanner, and then start up your applications again. So the beauty of this approach is its simplicity. However, most online databases can't be migrated this way because they can't tolerate the downtime. But if you can, seriously consider doing stop and copy. All right, the more common approach particularly for migrating online databases, is the so-called zero downtime approach. So in this approach, you first take a snapshot of your MySQL database and you start copying it over to Spanner. And while that's ongoing, you capture all of the real-time changes using change data capture, CDC. And you can either replay them to Spanner while the initial load is ongoing, or you can store the CDC stream and replay it after the initial load is complete. There are some trade-offs involved here, and there are also some important data consistency issues to get right. For example, if the initial load and CDC writes happen at the same time, you need to ensure that old data from the initial load doesn't overwrite incoming new data from CDC. In any case, when the initial snapshot load and CDC load are complete, there is a short period when you stop the MySQL database, let the CDC stream drain to Spanner, and then switch over applications to Spanner. This switchover time can be a few minutes to maybe tens of minutes. So there's some downtime, but it's typically fairly small. Another approach I want to briefly mention is dual writes. So in this case, you modify the application stack to write to both MySQL and to Spanner at the same time. So this also requires an initial load of data to Spanner and some synchronization between the initial load and the dual writes to ensure data integrity. Now, the main benefit of this approach is that it allows you to run both databases in parallel and to switch from MySQL to Spanner and back again if needed. However, this can be pretty costly in terms of resources, and there are some other really difficult technical issues to resolve, and that's around failures. So what happens if you're committing a transaction and the transaction succeeds in one database and fails in the other? How do you recover? I see the question. Let me postpone that till the end, and I'll get back to that question. Another approach is incremental migration. And this is not a fully general solution, but it can be really useful for some applications. And I've seen this used in a number of different contexts. So the core starting point is to have a highly partitioned database. So for example, the database might map IDs of some kind to data about those IDs, and where each ID is independent of other IDs. So in particular, we need for updates of the database to involve just a single ID. In other words, we don't have any multi-ID update transactions. Then what you can do is you can pick an ID, copy its data from MySQL over to Spanner, and that's usually pretty quick, maybe even a few tens of milliseconds. And then from that point on, you serve that ID from Spanner. And if needed, you can actually move this ID back from Spanner to MySQL. Now, the core of this approach is an ID to database mapping that has to be maintained so that you know at all times which database actually owns that particular ID. All right, the next step I want to mention in the design and implementation phase is application migration. And again, this is a really large topic, and I'm just going to touch on a few aspects. So the first is around application code changes. So what will be needed here is going to heavily depend on what drivers the application uses and whether an ORM is used. So some database users structure their applications around a database abstraction layer, which is an application-specific set of APIs that abstract the core operations needed from the database. And this can be a huge help for migration since it localizes the database-specific code to a small set of APIs. So now application migration can now focus on just rewriting those APIs or the implementation of those APIs to use Spanner. At the other extreme, some applications spread their database code throughout the application, and this can lead to really very time-consuming and complex code migrations. Now, we briefly mentioned before that MySQL and Spanner have different SQL query dialects. So each query used in an application needs to be checked and potentially rewritten to use with Spanner. So sometimes this is fairly straightforward. Sometimes it can be a huge amount of work. It depends on the structure of the application. Finally, I wanted to briefly mention stored procedures. These are not supported by Spanner, and the usual approach is to rewrite them as application code. All right, it goes without saying that testing is fundamental to a successful migration, and this can either use test traffic or parts of your production load. If it is test traffic, it's really very important to ensure that the test traffic realistically models the production setup. And if it's part of your production load, then it's really important that the part that you use be representative of your full load. And as I mentioned earlier, it's common for steps 3 and 4 to be intermixed. So you might have an initial design and an implementation, try it out, find issues, and then go back and do some redesign and change the implementation. Maybe you find performance issues, you need to tweak the schema, for example. So this is really an iterative process. All right. Now we come to the exciting part, actually doing the migration. So first, a quick comment. Not every migration will have a migration day. So for example, if you use incremental data migration, then your migration is essentially an incremental continuous process. It might have a start day and an end day, but that could be weeks, maybe even months apart. However, many migrations do have a target day for moving or completing data move and switching over to using Spanner. This becomes a really critical day. Here's where you find out if all of your planning and testing have been effective. And obviously, you really want migration day to be problem-free. Now, one of the very important aspects of migration day is knowing what to do if you run into problems. First, how do we know if things are okay or if there is a problem? What signals and dashboards should we be looking at? What thresholds are acceptable? Who is the decision maker for reverting? How do we revert? And it's critical that the revert process has been well tested. So one thing to consider, especially for gaming applications, is database warm-up. So for example, suppose we're migrating a game platform from MySQL to Spanner, and we're going to launch with a new game. So we've gone through all of the tasks of schema migration and application migration, but we don't actually have any data because this is a new game. So our tables are empty. Now, Spanner's load balancing mechanisms respond to load signals. And we'll talk about this in a little more detail later. But the point is that these mechanisms take time to respond to load changes. And generally, this is not an issue because they respond fairly quickly, on the order of a few minutes. But if the tables are empty, then it can take several iterations of this load balancing mechanisms before we can adapt to the full load of a game launch. So to address this, we need to warm up the tables. And basically, this is typically done by pre-populating the tables with synthetic data and adding load to stimulate Spanner's load balancing mechanisms. And then the synthetic data can be deleted. Now, if a database is already populated with data as part of a data migration, then warm-up is usually not needed because there's already enough splits and enough warm-up of the database because of the load of the data. All right. The next couple of slides are going to address some low-level details of migrations specifically from MySQL to Spanner. And I want to first have a look at types. So Spanner provides coverage of the core types of MySQL. However, you'll notice that where MySQL has many different integer types, for example, Spanner has just one, int64. So similarly for floating point numbers and for chars and text types. There's just one float type in Spanner and there's just one string type, although it's a string type, but it has a parameter with a length limit. Now, MySQL also has a variety of other types, such as geometry types, point, line, and so on. Spanner doesn't provide a corresponding type for these, and we usually recommend using either string or bytes here. Now let's dig a little bit into the design of primary keys. And in order to do this, I first need to talk about splits and their role, and then we'll come back and talk about best practices for primary keys. So some of the material here has already been covered in previous Spanner meetups, but I'll briefly recap the idea. So in Spanner, the primary key space of each table in a database is partitioned into chunks called splits. So in this example, the primary key is an integer, and the first split ranges from minus infinity to minus 100, the next split from minus 99 to 3000, and so on. So the same basic thing happens across other types, whether they be strings or floats, and also for multi-column primary keys. Now, each zone has a copy of each split. So I have a very simple layout here for a single region Spanner instance where we have 3 zones, zone A, zone B, zone C. And each zone has a copy of every split. So here's split 0 in zone A, here's split 0 in zone B, and here's split 0 in zone C. And they could be distributed somewhat randomly across the span servers in each zone. So the key point is that each zone has full coverage of the key space of a table, and indeed has a full copy of the table's data. So you can think of each zone as essentially a standalone replica, and Spanner ensures that each replica stays in sync and has exactly the same committed data. So what's the role of splits? Well, there are really 2 parts to this. The first is that splits are the basis for distributing table data across span servers. And the second is that they form a core part of an automated sharding mechanism to balance load across span servers. So splits are not static, unlike in many other databases and sharded databases. So in Spanner, splits are not static. They're continually on the move and they're continually evolving. So for example, if a split is hot and receiving lots of load or contains lots of data, it'll be split into smaller splits. And if 2 neighboring splits have been relatively inactive for a long time, then they'll be merged. So the core ideas behind splits were actually developed as part of Bigtable many years ago, and they've been adopted and extended to form a core part of Spanner. Now, based on our understanding of splits, we can come back to the question, what makes a good primary key? And very simply put, a good primary key is one that spreads the key values over the key space. So names are usually a good primary key, unless everyone has the same name or very similar names. And hashes are also an excellent primary key. What we want to avoid is primary keys that clump together some aspect of the life cycle of table rows, whether that be creation of rows or updates and reads or deletions. So for example, auto increment keys are problematic because with auto increment, all new rows will be in exactly the same part of the key space. So this will cause a hotspot for row creation, for inserting into the database. And in fact, with auto increment, they'll actually appear in the same split and it'll be on the same span server. So more generally, we want to design our primary keys to avoid hotspots. I mentioned several tools for assisting with migration, and I'm going to conclude with a little more detail of these tools and their capabilities. I've mentioned Harbour Bridge several times. So Harbour Bridge is an open source tool. It's used for various stages of migration. It can be used for assessment, can be used for schema migration, for data migration. So here's a sample workflow where Harbour Bridge is run and it ingests data from a MySQL or Postgres database. And we can either use dump formats like MySQL dump or PG dump, or directly access the database using select queries and extract schema information using information schema tables. It builds a Spanner schema, creates a database and populates it with data from the source database. And then it documents that run with a detailed assessment report that includes potential issues with type mappings, highlights MySQL features that are used by the source database that are not supported by Spanner, and also logs any errors encountered. So Harbour Bridge can also be used to browse and customize your Spanner schema in what we call schema assistant mode. All right. The other two tools I want to highlight focus on data import. The first is a bulk data import tool. And this is part of our generic, Google's generic data flow service, which is a unified streaming and batch processing service. So this service supports bulk data import into Spanner, and supported formats include Avro and CSV. And the second tool I want to mention is a CDC import tool. So this is part of our generic data stream service, which is a change data capture and replication service. And this service supports MySQL to Spanner CDC, amongst other combinations. Now, let me stop here, and many thanks for your attention. And I'll invite questions and comments. And let me go over to the chat. And I think there was at least one question there. From Andrew. All right. All right. So Andrew asks, would you advocate any small-scale migration testing using the Spanner emulator? So actually two questions. Let me talk about the emulator. So the emulator is a really fantastic piece of technology for testing things out, and testing out functionality. I would be careful though of what if you're doing a migration, then you're typically want to understand throughput and performance issues, and the emulator is not going to help you with those. So view the emulator as a really faithful reproduction of Spanner's functionality. So for testing code, testing different scenarios, but usually in a migration, as I said, you're really interested in understanding scalability, throughput, and performance, and the emulator is not going to be able to help you there. So, a qualified yes, definitely use the emulator where it's appropriate, but I would not encourage using the emulator as your only testing environment for migration testing. Okay, how would you handle application code changes for transactions that hit the 20K mutation limit? Yeah, that's an interesting question. So I guess I have a question in response, and that is there are a number of other tools that we have for doing large-scale mutations, and in particular, we have ways of doing partitioned DML. Now, the partitioned DML is typically used when you want to make a large-scale change across the entire database. And the partition DML allows you to basically carve up the overall operation that you want to do into smaller pieces. And so that way, we get around the 20K mutation limit because we're actually splitting up the operation into multiple transactions. Now, so if you can use it, partition DML is definitely a very convenient tool and will solve the problem you have. The main constraints around partition DML are the restrictions on what kinds of DML operations you can use it for. So if you've got something that you can't use partition DML, then the main operation, or the main approach that's open to you, is to basically split it up into smaller sets of mutations. So basically split it up into smaller transactions. And that may require some code change or some manual teasing apart of this large operation. So, maybe Andrew, do you have some more background you can give on the particular use case that you have? Okay. All right. And Andrew also mentions, okay, no problem. Andrew also mentions the data streaming space. There's a Debezium. All right. Any other questions live, or anything anyone wants to either ask about or to give feedback on? Yes. Eswara asks, will there be any SQL rewrite required from MySQL to Spanner? Yeah, I mentioned that part of migration from MySQL to Spanner can potentially involve having to rewrite SQL queries. Spanner and MySQL have somewhat different SQL dialects. And so, if you're using very basic SQL constructs, those may well be fairly easy or maybe not require change at all. But it's quite common for MySQL applications that use a lot of different SQL constructs that requires a lot of a substantial amount of rewrite. Okay, so the follow-up question: how much percentage we need to cover up on the migration strategy? Not quite sure not quite sure I follow the question. Do you mean how much of is the query rewrite of the migration, or are you referring migration? Eswara, do you mind clarifying that? Oh, to SQL rewrite. Yes. That depends tremendously on the particular application. So I have seen application migrations where the SQL rewrite was very straightforward, and particular applications that were organized around some sort of database abstraction layer. I've heard a number of Spanner users who were very easily able to move from MySQL over to Spanner from a query perspective. But I also know customers who have spent a substantial amount of time on this. So it's hard to give an exact percentage because there's a huge variation across different customers. So I think it's some good starting points in estimating this are around, well, how many different queries do you have, and how many different kinds of queries, and what kinds of features of Spanner are those? What kinds of features of MySQL are those queries using? And then look to see at how the features that you're using in your MySQL queries, how those features map onto Spanner features. So if you're doing very simple things like standard selects, then that's going to be very easy to migrate over to Spanner and may not require any changes at all. If you're using a lot of internal MySQL operations, so built-in functions. If you're using a lot of built-in functions, then you'll need to see how they map over to Spanner. Sometimes the syntax is completely identical. Sometimes for built-in functions, there are variations in the naming of the built-in functions, and some built-in functions of MySQL are not supported in Spanner. So that's another aspect to look at. So look at the queries that you have and look at the features that you're using in MySQL. All right, Andrew follows up to the earlier question. I'm thinking mostly around third-party applications or ORMs, where one can't as easily control the size of the transaction. Yeah, look, I agree with you. This is an issue. And we're more than happy to work with you on finding solutions and understanding more about it. We recognize that this is an issue and something that we're working on to increase the limits. We don't have any commits, we don't have any dates, we don't have any announcements on this, but we're well aware of the issue. So Andrew, I definitely strongly encourage you to interact with the Spanner team, either with me or other people in the Spanner team, or with your point of contact on the sales side. We'd love to hear more about the problems that you're having. And I completely agree. When you're using a third-party tool or an ORM, you often don't have the control over this. So yeah, please get in touch with us, and I think it'll depend on the specifics of the problem that you have. All right. Any other questions? Thank you, Eswara and Andrew. All right. Well, thank you everybody for attending. And I think if there are no other questions, we will wrap it up. Thanks. And thanks, Roy, for hosting.
Absolutely. Thank you, Nevin, and thank you everyone for joining. I will end the recording right now. Thank you all.